All right, this is the video for lesson 6.1 for Discrete Math. And I'm going to try and fit this whole lesson in one video and hope that I don't get interrupted too much during this video. So section 6.1 is about Markov chains, and this is actually ties into some stuff that you've seen earlier in the semester. So first of all, a Markov chain is a process that arises in problems that involve a finite number of events that change over time. So we're going to look at this situation here. So it says a food service director at a high school conducted a survey in hopes of predicting the number of students who will eat in the cafeteria in the future. The results are as follows. If a student eats in the cafeteria on a given day, the probability that he or she will eat there again the next day is 70%. If a student does not eat in the cafeteria on a given day, the probability that he or she will eat in the cafeteria on the next day is 40%. Suppose that on Monday, 75% of the students ate in the cafeteria and 25% ate elsewhere. What can be expected to happen on Tuesday? Represent the situation using a tree diagram below. So we did some of this earlier on in the year. So we'll start with Monday. In Monday, we know that 75% ate in the cafeteria, so 0.75 were in the cafeteria. Which means that 25% or 0.25 ate elsewhere. And again, that's for Monday. Now, based off of that, they tell us this information up here, that if a student eats in the cafeteria on a given day, the probability that he or she will eat there again the next day is 70%. So out of these people that ate in the cafeteria on Monday, when they go to decide where to eat on Tuesday, 70% of them, so 0.7, will again choose the cafeteria. So that's on Tuesday, which means that 30% of those people that ate in the cafeteria on Monday choose to eat elsewhere. Now that second bullet up above tells me if a student does not eat in the cafeteria on a given day, the probability that he or she will eat in the cafeteria the next day is 40%. So this branch is going to be 40% end up going to the cafeteria, and that means that 60% are going to go elsewhere. So just like we did earlier in the semester with these tree diagrams, we're going to multiply these probabilities for each branch. So the 0.75 times 0.7 gives me 0.525. And that, remember, is the probability of cafeteria and cafeteria. Okay, so both days. The next branch, I have to do 0.75 times the 0.3, which gives me 0.225. And again, that was probability of eating in the cafeteria and then eating elsewhere the next day. Now I'll start with elsewhere and cafeteria, so 0.25 times 0.4 gives me 0.1. So again, that was elsewhere and then cafeteria. And then the last one, I have the 0.25 times the 0.6. So again, we're multiplying the probabilities on the different branches. This gives me 0.15, which is the probability of eating elsewhere and then eating elsewhere again. So we want to know what can be expected to happen on Tuesday. Okay. On Tuesday, it looks like we can expect for the cafeteria workers can expect to have 0.525 plus 0.1. So that's going to be 0.625 in the cafeteria. And if we look at elsewhere, it's 0.225 and 0.15, which gives me 0.375 eating elsewhere. So the cafeteria workers can expect to see about 62.5% of the students that they'll have to feed, and it looks like about 37.5% of the students will have to eat elsewhere. All right, so this leads us into transition matrices, which we have seen a little bit earlier this year as well. It says the Monday student data are called the initial distribution of the student body and can be represented by a row or initial state matrix D sub 0. They want us to write that below. So D sub 0, remember a row matrix just has a single row and rows go across. The Monday population, the Monday data is what we want in this row matrix. And we said up above that on Monday, 75% of students eat in the cafeteria. So I'm going to put 0.75 for cafeteria. And for elsewhere, we had 0.25. And again, that comes from the information they gave us or the information for that initial day in our cafeteria. All right, when we move from one state to another, we call it a transition. So the data about how students choose to eat from one day to the next can be written in a matrix called a transition matrix, T. And we want to write matrix T below. So we want a matrix T that shows how students move from one state to another. So transition matrix T is going to be a square matrix, so same number of rows and columns. And to stay consistent with what I had before, I'm going to do C and then E, so cafeteria and then elsewhere, both for the row and the column. And this comes from our information in the bullets above. It says if a student eats in the cafeteria on a given day, the probability that he or she will eat in the cafeteria again the next day is 70%. So cafeteria on Monday, going to the cafeteria on Tuesday is 70%, so 0.7. Again, that means going from the cafeteria to elsewhere would be 0.3. And then students that eat elsewhere on Monday, going to the cafeteria on Tuesday, okay, on that next day, is going to be 40%, so 0.4, which means students that eat elsewhere and then eat elsewhere the next day has to be 0.6. Remember, these rows have to add up to 1 to account for 100%. All right, so I'm going to go ahead and turn to the next page here. It says all of the entries in these matrices are probabilities. So their values will always be between 0 and 1 inclusive. Inclusive just means that you can include that number. These matrices are also always going to be square matrices, where the sum of the probabilities in any row is always 1. So that's kind of an important piece of information to be aware of. The sum of any row is always going to be 1. All right, so number 1, they want us to calculate the product of matrix D sub 0 and matrix T. So remember, you are going to do this on Desmos. You can go to desmos.com/matrix. In fact, let me write that here. desmos.com/matrix. You can use your graphing calculator as well if you know how to do matrices on there. So they want us to multiply those together, and I'm going to write down what each of the two matrices were just so we can see them. And if you wanted to do it by hand, you could, but again, I would probably just use the calculator on this. So d sub 0 times t. Let me just jot this down. D sub 0 from the previous page was our row matrix that was 0.75 and 0.25. And then T was the matrix we just had on the previous page where we had 0.7, 0.3, 0.4, and 0.6. So if we do D sub 0 times T, we have a 1 by 2 matrix times by a 2 by 2 matrix. That's going to give me a 1 by 2 matrix for my answer. And if you do this correctly on Desmos or your calculator, you should get 0.625 and 0.375. And again, this is cafeteria and elsewhere if we stick to the same order that we've been using. So number 2 says, compare these calculations to your tree diagram on the last page. Well, on the last page, if you look at your tree diagram, what we said was going to happen on Tuesday. Let me actually flip back there. We wrote down here what we expected to happen on Tuesday. And if you notice, those are the same numbers that I got when I multiplied d sub 0 times t. So we ended up with 0.625 or 62.5% eating in the cafeteria and 0.375 eating elsewhere. All right, problem number 3. It says the values in the resulting row matrix can be interpreted as the portion of students who eat in the cafeteria and who eat elsewhere on Tuesday. Label your new matrix D sub 1. So this matrix we came up with here, it's still on the screen. This matrix that we came up here, D sub 0 times t, that's also just equal to D sub 1. That's what they want us to call that. So I'm going to just jot this down here, that D sub 1 is 0.625 and 0.375, again for cafeteria and elsewhere. All right, for 4, to make a prediction for Wednesday, what two matrices should we multiply? Well, if taking d sub 0 and timesing it by the transition matrix moves us from Monday to Tuesday, then to get from Tuesday to Wednesday, we should multiply d sub 1 times our transition matrix. And let's see, I think that's all they're asking me for there is which ones I should multiply. And then number 5, determine the values in our new matrix D sub 2, our predicted number of students eating in the cafeteria on Wednesday. So now they want me to actually do D sub 1 times T. So again, use your calculator, use Desmos to help you multiply that out. But D sub 1 times T will give me D sub 2, which should come out, if you do this correctly, to 0.5875 and 0.4125. Again, for the cafeteria and elsewhere. All right. Just about done here with our notes. So number 6, consider how D2 is calculated. D2 we found by doing D sub 1 times T. But d sub 1 was d sub 0 times t. So it says use substitution to show a new calculation for d sub 2. So they want us to use these to find what's another way I could find d sub 2. Well, if d sub 1 is d sub 0 times t, I could plug this in for d sub 1 and say that d sub 2 is just taking d sub 0, timesing it by t, and then timesing it by t again. Well, you know that t times t would give me t squared. So kind of a shorter way to do this is to take d sub 0 and times it by t squared. Remember, d sub 0 was our initial matrix that we had from, was that on the previous page? Yeah, from the previous page. It was our initial distribution. So on Monday, 75% of students ate in the cafeteria, 25% ate elsewhere. So that's what made up matrix D sub 0. And then this t squared is our transition matrix. So to get from Monday to Wednesday, we transitioned 2 times, so I had to square the t. All right. And then based on this new formula, how could I find the distribution for lunch in the cafeteria on Friday, which would be day 4? Well, if I want day 4, that's just going to be day 0, so d sub 0 times t to the 4th power. We're transitioning from Monday to Tuesday, Tuesday to Wednesday, Wednesday to Thursday, and Thursday to Friday. So on the calculator, again, on your Desmos calculator, I want you to put in the matrix d sub 0, times it by our transition matrix raised to the 4th power, and that should come out to 0.572875 and 0.427125. Again, for cafeteria and elsewhere. Now, I did this on a graphing calculator. I don't know on Desmos if it gives you quite this many decimals. If it does, great. If it doesn't, go out as far as what they will give you. And then our last step here, it says instead of using transition matrices, we can also show the movement of students in a weighted digraph called a transition digraph or a state diagram. Show a transition digraph for our cafeteria stats below. So this is, again, tying into something we did in a previous chapter. We have 2 vertices. Those vertices would be, I'll use C for cafeteria, and I can put E for elsewhere. And again, the people that eat at the cafeteria and then go back to eat at the cafeteria the next day. Let's see. I gotta flip on my other sheet here. So if you ate at the cafeteria on the first day, there's a 70% chance that you eat there the next day, so this would be 0.7. There's a 30% chance that you would eat elsewhere. So I'm gonna draw an arrow against a digraph, so we need an arrow to show the direction. So cafeteria the first day going to somewhere else is gonna be 0.3. If you eat elsewhere on the first day, there's a 40% chance that you're going to the cafeteria the next day. And if you eat elsewhere on the first day, there's a 60% chance that you'll eat elsewhere again the next day. All right, and I believe that is it for section 6.1. So if you have any questions, just be sure to let me know.